Welcome everyone. In this video, we're going to look at how the Maxwell-Boltzmann distribution can be used to show the impact on reaction rates due to an increase in temperature. If you haven't come across the Maxwell-Boltzmann distribution before or need a quick recap, check out my introductory video, the link is in the description. Let's get started with a worked example. Label the axis and sketch a Maxwell-Boltzmann distribution curve. The y-axis should be labelled number of particles or number of molecules with a given energy. This is often abbreviated to number of particles. The x-axis shows energy. 0 particles have 0 energy, so the graph must start at the origin, 0, 0. The number of particles then rises with energy until a maximum is reached. This is the most common energy. The number of particles then decreases but never touches or crosses the x-axis. We say that the number of particles tends to 0. The area beneath the curve represents the total number of particles. Here's another example question. Annotate the distribution with activation energy EA. Shade the area that represents the particles that can react. Activation energy is the minimum energy needed for a collision to be successful. That is, a collision that results in a reaction. Most particles do not possess the activation energy. Most collisions do not result in a reaction, so EA lies quite far to the right of the x-axis. The area to the right of EA beneath the curve represents the particles that can react. This is shaded in blue here with a clear label showing what is represented. This is always a good technique to use in exams. Let's look at the impact of temperature on the distribution of energies. Remember, the area beneath the curve represents the total number of particles. If the same sample of particles is heated up, the total number of particles stays the same, but the energy of the particles increases. The blue dotted line on the graph intersects the x-axis at the most common energy for this temperature. The red line represents the distribution of energies at a higher temperature. The red dotted line intersects the x-axis at the most common energy for the higher temperature. For the same sample of particles at a higher temperature, the area beneath the curve must be the same. The most common energy and average energies are higher. The higher temperature line only crosses the lower temperature line once. Here's the final example. Annotate the Maxwell-Boltzmann distribution shown below with a second curve to show the distribution of energies of particles in the same sample at a higher temperature. Explain why a small increase in temperature results in a much faster rate of reaction. In an exam, this question will be worth about 3 marks. We add the second curve showing the distribution of energies at a higher temperature. Ensure that the area beneath the second curve is approximately the same as the area beneath the original curve. The peak of the second curve must be lower than the peak of the original curve, i.e. there are fewer particles with the most common energy. We can address the next part of the question by annotating the graph. It is a very good idea to do this in exams given the opportunity. First, we label the activation energy EA. Next, we shade in the particles that can react at a lower temperature with a clear label. We can then use a different pattern of shading to represent the additional particles that can react at a higher temperature. Always read the question and address the question very clearly. We are asked to state why there is a much faster rate of reaction at a higher temperature. Increasing the temperature increases both the likelihood and energy of collisions, so there are many more frequent successful collisions at a higher temperature. Thanks for watching. I hope you found the video useful. Please post any comments if you have any questions or suggestions. Check out the main website www.flipchem.com. Login details are in the description. You can also email info@flipchem.com for a free username and password. Take care and good luck with your studies.